Hello, Professor WNTS. My name is Giovanno Zhong, and now I'm going to explain topic one. So, number one, I'm going to find the RT first. So, RT equals to T times YT, and the YT equals to Y0 times 1 minus T to the power of E. So, T times Y0 times 1 minus T to the power of E. And the answer for RT is Y0 T times 1 minus T to the power of E. Next, I'm going to explain the lever curve. So this is the lever curve I've drawn before. So the tax revenue is on the y-axis, while the tax rate is on the x-axis. So at first, the lever curve rises initially, but eventually declines. And this I have drawn the dotted line in the middle of the curve like this, and the T star on the top of the curve like this. So the full explanation is tax revenue rises at first because increasing the tax rate boosts the amount collected from each unit of income, while taxpayers still work and earn roughly the same amount. However, as the tax rate becomes too high, people reduce their work effort, shift income, or engage in avoidance and evasion, causing taxable income to shrink. Once these behavioral responses outweigh the effect of the higher tax rate, total revenue begins to fall, explaining why the labor curve rises initially but eventually declines as the tax rate approaches 100%. Next, the reduction in working hours or labor participation will lead to when the net of tax rate falls, people choose to work less, while legal tax avoidance will lead to stronger incentives to use loopholes, defer income, or shift income into firms with lower tax burden. Next, the tax evasion will lead to illegal underreporting or hiding of income increases when tax rates are high. And last, tax base shifting will lead to movement of capital across countries or shifting the timing of income, such as accelerating or delaying reporting. Next, number two, I'm going to find the first derivative of RT. So R accent T equals to Y0 times 1 minus T to the power of E plus Y0 T times E times 1 minus T to the power of E minus 1 times minus 1. So this I'm using the product rule. Next, Y0 times 1 minus T to the power of E minus 1 times 1 minus T minus ET. And next, I'm going to rewrite the previous equation like this, Y0 times 1 minus T to the power of E minus 1. But now I'm going to open the bracket here. So like this, minus 1 minus T minus ET to the equals to 0. Since this equation cannot be equal to 0, so I'm just going to use this equation only. So like this, 1 minus T minus ET equal to 0. And let's move the minus T minus ET to the right. So 1 equals to T plus ET. And let's open and let's let's put the T outside the bracket. So like this, 1 equals to T times 1 plus E, like this. So the T star equals to 1 per 1 plus E. So this is the T star. Next, I'm going to find the second derivative of RT. So R accent T equals to Y0 times E minus 1 times 1 minus T to the power of E minus 2 times minus 1 times 1 minus T minus ET plus Y0 times 1 minus T to the power of E minus 1 times minus 1 minus E. Next, Y0 times 1 minus T to the power of E minus 2 times E minus 1 times minus 1 plus T plus ET plus 1 minus T times minus 1 minus E. Next, y0 times 1 minus t to the power of e minus 2 times minus e plus et plus e squared t plus 1 minus 1 minus e plus t plus et. Next, y0 times 1 minus t to the power of e minus 2 times minus 2e plus 2et plus e squared t plus t. Next, I'm going to find the r accent 1 per 1 plus e. So y0 times 1 minus 1 per 1 plus e to the power of e minus 2 times minus 2e plus 2e times 1 per 1 plus e plus e squared times 1 per 1 plus e plus 1 per 1 plus e. Like this. Next, y0 times e per 1 plus e to the power of e minus 2 times minus 2e times 1 plus e plus 2e plus e squared plus 1 per 1 plus e. Next, y0 times e plus 1 plus e. I mean e per 1 plus e to the power of e minus 2 times minus e squared plus 1 per 1 plus e. Next, y0 times e per 1 plus e to the power of e minus 2 times 1 minus e. So this equation is positive. Sorry, this equation is positive, while this equation is also positive, and the last equation is negative. So in conclusion, r accent 1 per 1 plus e is less than 0, so it is maximum. Next, I'm going to explain number 3. So the elasticity of taxable income measures the percentage change in taxable income y resulting from a percentage change in the net of tax rate. While the economic meaning is a higher elasticity means taxpayers are more responsive to tax increases, they reduce their taxable income more aggressively through lower labor supply, tax avoidance, evasion, or shifting income. A low elasticity means taxable income barely changes when tax rates change. Next, I'm going to find this one. So number 3, t star equals to 1 per 1 plus e, like this. If the e equals to 0.2, so the t star equals to 1 per 1.2, or equals to 0.8333, or it is 83.33%. While if the e is 1, so that means the t star equals to 1 per 2, or 0.5, or 50%. While if the e is 2, so the t star equals to 1 per 3, so the answer is 0.3333, or 33.33%. When the taxable income responds strongly to tax increases, the government must set a lower tax rate to maximize revenue. Otherwise, taxpayers reduce taxable income too sharply. But if the taxable income is relatively insensitive to tax changes, the government can set higher rates without significantly reducing the tax base. That's all from me. Thank you.
So now I'm going to explain about the topic 2, which is the firm's demand, cost, and profit maximization. So we are given a demand and cost function. The first one is the price of Q equals to 100 minus 2Q, and then the cost function is 100 plus 2Q plus 20Q plus 0.5Q squared. So first thing we need to find is the revenue function. First we write revenue of Q equals to Q times the price of Q, and that's equals to Q 100 minus 2Q goes to 100Q minus 2Q squared. And then next we need to find the profit function. Pi, the pi of Q equals to R Q time minus C of Q. And then once we get the revenue and the profit function, we need to substitute it. So we need to substitute it to pi Q equals to 100 Q minus 2Q squared, and then minus 100 times 20Q plus 0.5Q squared. And then we simplify it, and that's equals to 2.5Q squared plus 80Q minus 100. And okay, we found the profit. We have found the profit function. So now we need to find the derivative that we need, and that is the marginal revenue and also the marginal cost. And so how do we get the marginal revenue? So marginal revenue equals to the derivative of the revenue, derivative revenue, and that's equals to 100 minus 4Q. And for the MC, which is the marginal cost, it's from the derivative of the cost function. So it's 20 plus Q. Yep, 20 plus Q. Here I also illustrate the graph, which is the P curve is downward sloping, and the marginal revenue is lies below it, and it is more steeper, and the marginal cost is upward sloping. So now we need to find the profit maximizing quantity. So first, the profit maximizing quantity is the derivative of pi of Q equals to marginal revenue minus marginal cost. So here we get 100 minus 4Q minus 20 plus Q. And that's equals to 80 minus 5Q. And Next, we need to set this equals to 0. So 80 minus 5q, and that's equals to 0. And the q is 16. The q is 16, and now we need to check the second derivative. So the second derivative of pi at q minus 5 is less than 0. Profit at q is indeed maximized. 16 equals to 100 minus 2, 16 pi 16 equals to 100. 16 minus 2, 16, 100, 5, 16 square. The total will be 540. So the firm's profit maximizing quantity is 16, and the price 68. Profit is 540. And so R, the derivative of R, Q equals to MR. So we need to input the numbers. It's the 100 minus 4Q equals to 0, and the Q is 25. And now we need to check the second derivative from mu, and that is the minus 4, negative 4 less than 0. So basically revenue is maximized at 25 units. And now we need to input the function, the 25 into the function. So the price function goes to 100 minus, and that's equals to 50. Revenue, we need to put the 25 into the revenue function. So R 25 equals to R P 25 times 25, and that's equals to 1250. That's equals to 1250. So basically, the profit maximizing and revenue maximizing quantities are different because of the firm's objectives, where the profit maximizing firms chooses the output level where marginal revenue equals to the marginal cost, and ensuring that producing one more unit would no longer add to profit. Whereas the revenue maximizing is revenue maximizing firms produce until the marginal revenue equals to falls down to 0. Since this is the point where total revenue reaches its peak regardless of cost. So as a result, the revenue maximizing quantity is always greater than the profit maximizing quantity. Now we move on to the average cost. that equals to the cost of Q divided by Q, and that equals to 100 plus 20Q plus 0.5 Q squared. We divide it to Q with Q. And we simplify this to AC of Q 100 Q plus 20 plus 0.5 Q. And now to find the quantity minimizing average cost, we need to write down the derivative of the cost, the average cost. And it is 100Q, the power of -2 plus 0.5 goes to 0. Now we need to rearrange this into 100 divided Q2 equals to 0.5. And the Q square is 200, so the Q is 10 roots 2. Now let's check the second derivative of average cost. So cost Q goes to 200 divided by Q cubics, and it's less than 10. So this is minimum function goes to MC 2, so it's equals to around 34.142. Equals to 20 plus 0.5 Q. And since the second derivative of average variable cost is 0.5 less than 0, so its minimum occurs at Q equals to 0. And average variable cost is always increasing, and so both average variable cost and the marginal cost is both equal 20. In the final graph, it shows the marginal cost, average cost, and the average variable cost. The marginal cost cuts at its minimum, and the average variable cost lies below the average cost, and the average variable cost increases steadily because its slope is positive. And the marginal cost starts at 20 and increases linearly. So that's all from my explanation. Thank you for listening.
Hello, Professor Wu and TAs. My name is Sun Fei-sen. I'm from 國貿系, and my student ID number is 114301004 and 7. So today I'll be presenting to you the calculus video presentation, topic 3. So let's start with the first question. It'll be, what functional form does this utility function represent? The answer would be the Cobb-Douglas utility function with equal components, or the symmetric Cobb-Douglas. It implies interior solution and constant expenditures shares. So here each goods gets half of the income. For the next question, we are asked to use partial derivative to find the marginal utilities of x and of y. So here's the answer. For the MUX, it'll be 0.5x minus to the power of minus 0.5 times y to the power of 0.5. So to simplify it, I'll just write it using 1/2 x to the power of minus 0.5 times y 0.5. And do the same for the MYU, which is x to the power of 0.5 times 0.5 y to the power of minus 0.5. And we write it as 1/2 x to the power of 0.5 times y to the power of minus 0.5. The next one, which is number 2, is the consumer's budget constraint. This would be the function, which is 2x plus y equals to 100. Or you can rewrite it to 2x plus y minus 100 equals to 0. And then we were asked to set up the Lagrangian function for this optimization problem. So it'll be Lagrange x y lambda equals to x 0.5 times y 0.5 equals to lambda, and the budget constraint, which is 2x plus y minus 100. Okay, so for the third question, we were asked to solve the optimal quantities of good x and y. So for this one, we could just use the partial derivatives from partial Lagrange with respect to x equals to 1/2 x minus 0.5 times y with respect to 0.5 minus 2 lambda equals to 0. The next one would be partial Lagrange with respect to y equals to 1/2 x with respect to 0.5 times y with respect to minus 0.5 minus lambda equals to 0. And the last one would be minus 2x minus y plus 100 equals to 0. And now from this one, we can now find the x and y. To find the x and y, you can just do it like this. You can cross out the lambda and cross out the 1/2. And the result would be y per x equals to 2, and then y equals to 2x. So now we get the quantity of x, which is 25, and the quantity of y, which is 2x. So 25 times 2, which is 50. Now that we know the quantity of x and y, we can now compute it to the maximum utility, which would be u equals to 25 to the power of 0.5 times 50 to the power of 0.5 equals to 25 to, like this, maximum utility. So now that we know the x, y, and also the utility maximum, we can just find the equation of the indifference curve, which will be, we know that uxy equals to square root xy, and square root xy is equals to 25 square root 2, and you can just find the xy by square root both sides, which would results to 1250. So we can now know the indifference curve passing through 25 and 50, which would be y equals to 1250 divided by x. And this would be our graph. There's the tangency line here, and then there's the optimal bundle. And the blue line represents 2x plus y equals to 100, and the yellow line represents the indifference curve. So for number 5, we need to define the marginal rate of substitution, or MRS, which would be a rate at which the consumer is willing to give up y for a small extra amount of x while keeping the utility constant. Okay, so from this we could know that the MRS xy is equals to dy per dx, which means utility constant. For the next question, use the total differential to show why MRS equals to the ratio of marginal utilities. Because the utility function is u xy, and if you change x by a tiny bit, it will be dx. So du equals to partial u with respect to partial x times dx plus partial u with respect to y times dy, and this would be the total change in utility. And along the indifference curve, utility doesn't change, so we could rewrite it to mux times dx plus muy times dy equals to 2. And we can rearrange it to find the slope. So muy times dy equals to minus mux times dx, which would be dy per dx equals to mux per muy. And the MRS is the absolute value of the slope, so we know that MRS equals to mux per muy. Okay, so now we can find the slope. So for the budget constraint formula, we know that pxx per plus py equals to m, like this, and then we can rearrange it so that we can find the slope. So we can rearrange it to y equals to m per py minus px per pyx. So we can now know that the intercept would be m per py, and the slope would be minus px per py. And this would means that the opportunity cost of x in terms of y. So when you want one more unit of x, you must then give up px per py unit to stay on the budget. Use the constraint utility maximization condition to show that at the optimal point, the MRS equals to the relative price ratio. So we know that the MRS equals to mux per muy, and this shows our personal trade-off, like how we value x versus y, and the price ratio is px per py, which is the market's trade-off rate. So like how can you trade x for y? And at the optimal point, these two rates must be equal. And only when MRS equals to the price ratio is that you cannot make yourself better off by trading further. And this is the point where the tangency, it is a tangency point where the indifference curve touch the budget line, like that. And we can rewrite it and or rearrange it like this. So MUX per MUY equals to PX per PY, or MRS equals to the price ratio. For the next one, explain how the optimal quantities would adjust if the absolute value of the MRS is larger than the relative price ratio. So this means that the consumer values X more than the market does. We can write it like this. So MUX per MUY is larger than PX per PY. Which also means that the consumer will get more utility per dollar from X, so they will buy more X and less Y. And as they adjust, the MRS will fall until MRS equals to PY per PX, like that. Which will also restore the optimal tangency. And for the last one, how changes in income or prices would shift the budget constraint and affect the equilibrium. So when income increases, the budget line will shift outwards in parallel, and the consumer will move to a higher indifference curve, which would mean that they will buy more goods if normal. And then if the income decreases, the parallel will shift inwards, and the consumption will also decreases. For the price ratio, if the price of X increases, then the budget line would become steeper as it rotates inward, and the consumer will buy less X by then. And then when the price of X decreases, the budget line will become flatter, and the consumer would buy more X. And it is actually also the same for price changes for Y. As the higher PY, it'll rotate the budget line inwards around the y-intercept and reduces Y that is consumed. So that's it for the presentation for topic 3. I hope you can enjoy this presentation, and thank you for listening.